Now let's consider this question, question 7, in group 1 problems. It's to show that the set of all polynomials with rational coefficients is countable. So take some time to complete this yourself, and then wait a few seconds to get some hints, and after that we'll show you how to solve this. Alright, maybe you take a chance to try it out for yourself. And so for a hint, we're going to consider that if we want to prove that something is countable, we should be applying some theorems about the countability of sets. So we'll note that sets are countable if they are finite or if they're countably infinite. So your goal is probably going to be to show that this is countably infinite because clearly it's not finite. So what are some theorems you can use to prove that something is countably infinite? Alright, with that hint, you should be trying to think of using Cantor's diagonalization argument, which says that the union over some countable set alpha of sets that are themselves countable is also countable. So the way we do that is let's divide up the set of all polynomials. Let's partition them into sets A alpha, which are themselves countable. So but we'll first note that if we want to do that, we have to be using rational coefficients, since our first partition is obviously going to be the polynomials of the form a naught x to the 0, x to the 0 being 1. But a naught, if it was any real number, clearly we already have an uncountable set. So we must note that since we're using rational coefficients, we would have to prove first that the set of rational numbers is countable. That is another problem in this set of problems. So if you've already proven that, you can use it without proof. Otherwise, you should prove it yourself, that the set of rational coefficients is countable. With that, we will call this A0. Next, we'll generate the next set, which is all polynomials of the form A1 is equal to A naught plus A1 x to the first power, as you would naturally expect. And this, you'll note, is countable because it's made up of each of these coefficients has count options, and there are 2 of them. So you have a countable set because it's a union of two other countable sets. So again, by Cantor's diagonalization argument, this is countable. This generalizes. So for the nth set, which is of the form from I is equal to 0 up to n of ai x to the I, we have it that this is countable because you have n countable sets. So by Cantor's diagonalization, this is countable. So now we note that we have this for our index. Alpha is an element of the natural numbers, union with the 0, because we have one for each power of x, and we have polynomials to be taking into rational plus 0 powers. So we now have a countable set alpha of countable sets, namely each of the AIs we've shown to be countable. Therefore, by Cantor's diagonalization theorem, this is also countable, and we're done. Thank you for watching. Please like and subscribe.